Now 60% chance of the unexpected. In exactly 48 hours, something extraordinary happens that NASA has been quietly preparing for, and what you're about to discover might change everything you thought you knew about our place in the universe. An object traveling at 137,000 miles per hour from another star system will pass within 18 million miles of Mars, close enough to be studied in unprecedented detail by spacecraft orbiting the red planet. But here's what they're not telling you, what the mainstream media refuses to discuss, what makes scientists uncomfortable in public forums. Avi Loeb, the Harvard astrophysicist who shocked the world by suggesting Oumuamua might be alien technology back in 2017, has just rated this object a 6 out of 10 on his scale for potential extraterrestrial origins. That's 60% confidence, ladies and gentlemen. 60% scientific certainty that this isn't natural, that we might be witnessing something that could rewrite human history and our understanding of life in the cosmos. And when you see what amateur astronomers just photographed with backyard telescopes, images that professional scientists are desperately trying to dismiss and discredit, you'll understand why the scientific community is in absolute chaos right now, why conferences are being held behind closed doors, why data is being classified. Because this object isn't behaving like any comet we've ever observed in the entire history of astronomy spanning 4 centuries of careful observation. It's releasing pure nickel without iron, and that combination is physically impossible in nature according to everything we know about stellar evolution and cosmic chemistry. It only happens in industrial manufacturing processes where we deliberately separate metals for specific purposes. Its chemical composition is 16 times more extreme than any known comet, violating all our models of how these objects form and evolve. It turned from red to green overnight without any natural explanation that fits our understanding of comet behavior. And its trajectory through our solar system has a 1 in 500 chance of being random according to rigorous statistical analysis by multiple independent teams. That level of precision doesn't happen by accident in the chaotic environment of interstellar space. But here's where it gets genuinely terrifying, where this story transcends simple scientific curiosity and enters territory that keeps astronomers awake at night. In late September, 3IATLAS disappears behind the sun for 2 complete months. We won't be able to observe it during its closest approach on October 30th, when it should be brightest and most active. Earth will be on the opposite side of our star, completely blind to whatever happens during that critical period. Loeb suggests this timing could be intentional, not random orbital mechanics but deliberate positioning to avoid observation when something significant occurs. Some scientists privately believe it may have already deployed invisible precursor probes too small for Earth telescopes to detect, scout craft that could reach Mars while we're all watching the main object like a cosmic shell game. Over 227 observatories worldwide have tracked this thing with obsessive attention to detail. They've compiled over 4,000 individual observations using the most sophisticated equipment humanity has ever built, and every single data point makes it stranger, more anomalous, harder to explain with conventional comet models. At 33 billion tons, it shouldn't exist according to population statistics for interstellar objects. The mathematics simply doesn't work out. We should have found 100,000 smaller objects before encountering something this massive, yet we've only detected 2 previous interstellar visitors in all of human history. So what the hell is 3I/Atlas really? Is it an exotic natural comet from a dying star system billions of light-years away? Is it something artificial, something designed and launched with purpose? Or is it something we haven't even imagined yet? Something that doesn't fit into our neat categories of natural versus artificial? Before we dive deep into every shocking detail, every leaked observation, and every theory scientists don't want to discuss publicly because it threatens their careers and reputations, I need you to do something critical right now. Hit that subscribe button and turn on notifications because this story is developing in real time. New data is coming in daily from observatories around the world. The October 3rd Mars flyby could provide definitive answers or raise even more disturbing questions. You don't want to miss what happens next, and you definitely don't want to be left out of potentially the biggest scientific discovery in human history. This content represents hundreds of hours of research, analysis of technical papers, and interviews with scientists who agreed to speak only on background. Understanding this material will change how you see the night sky forever, so pay close attention to every detail. Leave a like right now to help this reach more people who need to understand what's happening above our heads. The algorithm needs to know this matters, that people care about real science and real mysteries. And I want you to comment below with where you're watching from, what time it is there, and whether you think we're alone in the universe. That engagement tells me you're paying attention, that you're part of this investigation, that you're ready for what comes next. Now let's get into the data that's making scientists lose sleep, starting with why Harvard's most controversial astrophysicist just went public with a 60% confidence rating that shook the scientific establishment to its core. Avi Loeb just did something that's sending shockwaves through astronomy departments worldwide, something that will either cement his legacy as a visionary or destroy what remains of his mainstream credibility. The Harvard astrophysicist who claimed Oumuamua might be alien technology back in 2017, enduring brutal criticism and professional isolation for that controversial stance, has now rated 3IATLAS at 6 out of 10 on his scale for potential technological origins. That's 60% confidence this isn't natural, not wild speculation or attention-seeking behavior, but a carefully calculated assessment based on hard data that any scientist can verify. And before you roll your eyes thinking this is just another crackpot theory from a once-respected scientist who's gone off the rails, understand what changed his mind this time around. It wasn't philosophical arguments about the statistical likelihood of extraterrestrial civilizations, though those arguments are compelling in their own right. It wasn't wishful thinking or a desire for fame and media attention. It was cold, hard data from the James Webb Space Telescope, the most powerful infrared observatory ever built, from the Very Large Telescope in Chile with its array of massive mirrors, and from Hubble, humanity's most famous eye in the sky. All three independent observatories are showing things that simply shouldn't exist according to 4 centuries of accumulated astronomical knowledge. Anomalies that demand explanation and refuse to fit into comfortable natural categories. Webb observed 3I/Atlas on August 6, 2025, using its near-infrared spectrograph, an instrument so sensitive it can detect the chemical composition of objects billions of miles away with incredible precision. What it found challenges everything we thought we knew about comet formation and evolution. The gas plume surrounding this object consists of 95% carbon dioxide and only 5% water, a ratio so extreme it violates all our models of how comets form in planetary systems. That's 16 times more extreme than any known comet at that distance from the Sun, an outlier so dramatic it shouldn't exist in our dataset. Think about that for a moment and let it sink in. Comets are supposed to be water-rich dirty snowballs because they formed in the cold outer regions of planetary systems where water ice was the dominant volatile material. Every comet we've ever studied from our own solar system, from Halley's to Hale-Bopp to dozens of others, shows that characteristic water-dominated composition reflecting the temperature and chemistry of our primordial solar nebula. This object is the complete opposite, fundamentally reversed. It's a carbon dioxide iceberg with barely any water, suggesting it formed in a radically different environment around a star with completely different properties in a protoplanetary disk with chemistry we've never encountered before. Then the Very Large Telescope detected something even more disturbing that professional astronomers are struggling to explain away. Strong, clear emission lines of nickel in the gas plume, signatures so unmistakable there's no ambiguity in the identification. Nickel atoms are streaming off the surface of this object, vaporizing as it approaches the Sun and heats up. But here's the detail that makes this truly shocking, the observation that keeps appearing in hushed conversations at conferences. There's no iron whatsoever, not a single emission line at any of the expected wavelengths where iron signatures should appear if this were a natural object. In the entire history of observing space objects since we developed spectroscopy in the 19th century, nickel and iron always appear together without exception, bound by the laws of stellar nucleosynthesis and supernova physics. They are forged together in the same nuclear fusion reactions deep inside massive stars burning through their fuel. When those stars explode as supernovas in spectacular deaths, nickel and iron are expelled together into space in predictable ratios determined by nuclear physics. They condense into dust grains together in the cooling ejecta. They get incorporated into asteroids and comets together during planetary system formation. Finding one without the other would be like finding oxygen without hydrogen in water molecules, a violation of fundamental chemistry that suggests something unnatural is happening. In every single meteorite that has fallen to Earth throughout recorded history, in every asteroid sample returned by space missions, in every comet we've analyzed spectroscopically, nickel and iron appear in lockstep with ratios that reflect their cosmic origins. But not here, not with 3I/Atlas. Only nickel, pure and isolated, streaming into space like exhaust from an industrial process. The VLT team, led by researchers who have absolutely no connection to Loeb's controversial claims and who would love nothing more than to debunk this anomaly, published their findings with extremely carefully worded conclusions that reveal their discomfort with the implications. They suggested the nickel might come from exotic nickel carbonyl compounds, theoretical molecules that could exist in the incredibly cold environment of interstellar space at temperatures just a few degrees above absolute zero. These compounds are volatile, meaning they break apart easily when exposed to ultraviolet light from the sun, releasing nickel atoms and carbon monoxide gas in a process that might explain what we're seeing. But even the VLT team admitted in the fine print of their paper that this explanation would be completely unprecedented in the annals of astronomy. It's never been observed in any solar system comet despite decades of detailed spectroscopic observations. It's never been detected in samples of interstellar space despite our best efforts to characterize the interstellar medium. It's a purely theoretical explanation invented specifically to account for an observation that desperately demands some kind of natural framework, however contrived. Here's what makes the situation even worse and more inexplicable. The nickel production isn't stable or gradual like you'd expect from natural sublimation of ices. When 3I/Atlas was first observed at 3.9 astronomical units from the Sun back in July, about 360 million miles away, the nickel emission rate was around 10 to the 21st atoms per second. That's significant enough to detect but not immediately alarming, possibly within the range of exotic natural explanations if you squint hard enough at the data. But by late August, when the object had closed to 2.85 astronomical units, still more than 260 million miles from the Sun, that emission rate had exploded 25-fold to unprecedented levels. 25 times more nickel streaming off the surface in just 1 month of approach. An exponential increase that doesn't match any comet behavior we've ever documented. The closer this thing gets to the Sun, the more dramatically its metal emission increases in a steep curve that looks less like gradual ice sublimation and more like systematic thermal processing of manufactured materials. It's as if layers of nickel-rich material are being vaporized by increasing solar heat in a way that natural geological processes can't easily explain. Loeb pointed out publicly what nobody else wanted to say explicitly in peer-reviewed journals where careers can be destroyed by speculation. On Earth, we separate nickel from iron routinely in sophisticated industrial metallurgy processes developed over centuries of technological advancement. High-purity nickel is used in specialized aerospace alloys for applications requiring specific thermal properties and resistance to oxidation. It's used in advanced electronics for its electrical conductivity and magnetic properties. It's used in batteries for energy storage. It's used anywhere we need metal with characteristics that iron alloys can't provide. The spectroscopic signature we're detecting from 3I/Atlas, that pure nickel emission without accompanying iron, matches industrial nickel production far better than it matches any natural cosmic process we understand. The separation of these elements in nature requires extreme conditions we only see in the most exotic astrophysical environments, and even then they end up mixed together again by the time they form solid objects. Critics immediately jumped all over this comparison with the ferocity of true believers defending orthodoxy against heresy. They said Loeb was cherry-picking data to support his predetermined conclusions, seeing patterns where none exist, engaging in motivated reasoning that starts with the answer and works backward to the evidence. Penn State's Jason Wright was particularly harsh in his public criticism, calling the comparison to industrial processes misleading and fundamentally unscientific, arguing that anomalous observations should be explained by extending natural models before invoking extraordinary explanations. Tom Statler from NASA's Planetary Science Division was even more dismissive in official statements, insisting that 3I/Atlas looks like a comet, acts like a comet, and does all the things comets normally do, so why complicate matters with wild speculation about artificial objects? Just apply Occam's razor and move on with real science. But here's what these critics conspicuously aren't addressing in their rebuttals and dismissals: the elephant in the room that everyone sees but nobody wants to acknowledge. If the nickel is coming from natural carbonyl compounds formed in interstellar space, as the conservative explanation suggests, then where the hell is the iron that should be right there alongside it? Iron forms chemically similar volatile compounds under the same conditions. Iron pentacarbonyl is well studied in terrestrial chemistry labs, stable at low temperatures, volatile at higher temperatures, breaking down to release iron atoms and carbon monoxide just like nickel carbonyl. If the extreme conditions of interstellar space somehow created and preserved nickel carbonyl molecules through billions of years of cosmic evolution, traveling through the galaxy at nearly absolute zero temperature, then those exact same conditions would inevitably create iron carbonyl molecules in comparable abundances. Both compounds should be present in the spectra. Both metals should be streaming off the surface as the object heats up approaching the sun. But only nickel appears in the data, isolated and pure, defying every model of natural chemistry we've developed. The VLT observations also detected something else that adds another layer to this mystery: rapidly rising production of cyanide compounds. Hydrogen cyanide and related molecules are appearing in the gas envelope around 3I/Atlas at rates that increase steeply as the object approached the sun through August and September, following the same exponential curve as the nickel emission. Loeb suggested in his blog posts that the dramatic color change amateur astronomers observed, that shift from red to green that happened seemingly overnight, might be connected to this sudden spike in cyanide production. When cyanide molecules absorb ultraviolet sunlight, they emit characteristic green light through a process called fluorescence, potentially explaining the vivid color transformation that dozens of observers documented independently. Now, cyanide itself isn't particularly unusual in comets, not something to get excited about under normal circumstances. It's a common organic compound found in many icy bodies throughout the solar system, a combination of carbon and nitrogen that forms readily in cold environments rich in these elements. But the rate of increase we're seeing with 3I/Atlas, that steep production curve that matches the nickel emission timeline, suggests these chemical processes are somehow linked in ways we don't fully understand. What's really fascinating when you dig into the implications is what all this data tells us about the object's fundamental composition and origin story. If most of the mass consists of carbon dioxide ice with only trace amounts of water as Webb discovered through detailed spectroscopy, and if the surface is simultaneously outgassing nickel and cyanide at exponentially increasing rates that defy simple models, then we're looking at chemistry that doesn't match anything formed naturally in our own solar system under the conditions we understand. Comets from the Oort cloud or Kuiper belt, those icy remnants left over from our solar system's formation 4.6 billion years ago, are consistently water-rich because they formed in regions where water ice was thermodynamically stable and abundant. The ratio of water to carbon dioxide in these objects directly reflects the temperature profile and chemical composition of the protoplanetary disk where they originated, giving us a fossil record of conditions in the early solar system. 3I/Atlas has the completely reverse ratio that shouldn't exist in our cosmic neighborhood. It's carbon dioxide dominant with minimal water, a composition suggesting it formed in a very different environment around a very different type of star, perhaps an old red dwarf with different nuclear burning processes, or in a protoplanetary disk with radically different chemistry than what produced our own planetary system. Or, and this is the possibility that makes mainstream scientists deeply uncomfortable, it suggests this object isn't entirely natural in the conventional sense. There's a third possibility that nobody wants to discuss seriously in peer-reviewed literature where everything you publish follows you forever, a middle ground between natural comet and artificial spacecraft that might be closer to the truth than either extreme. What if 3I/Atlas started as a completely natural object, an ancient comet ejected from its parent system billions of years ago and condemned to wander through the dark between stars for eons? What if it's been traveling through interstellar space for so unimaginably long that its surface chemistry has been fundamentally altered by processes we've never studied because we've never had access to objects this old? Constant bombardment by high-energy cosmic rays, the most energetic particles in the universe, could trigger nuclear reactions in surface materials over billions of years. Countless micro-impacts with interstellar dust grains traveling at relative velocities of hundreds of kilometers per second could physically and chemically alter the outer layers through shock heating and mixing. Exotic chemical reactions might proceed at glacial rates in the near-absolute zero void, reactions that would be impossible at higher temperatures but become favorable in the extreme cold of deep space. 7 billion years of continuous exposure to these conditions, longer than our entire solar system has existed, could theoretically do very strange things to surface composition in ways we've never imagined because we've simply never encountered materials this ancient and this traveled. Maybe the nickel without iron signature is completely real and accurately measured, but the explanation exists somewhere in that unexplored middle ground between ordinary comet and designed spacecraft. Maybe we're seeing the chemical fingerprint of processes that only occur in the deep time of interstellar travel, conditions so extreme and so prolonged that they produce signatures we've misinterpreted as artificial because we've never seen natural objects this old and this far from home. The October observations will provide crucial constraints when HiRISE aboard the Mars Reconnaissance Orbiter images 3I/Atlas from its position orbiting the red planet. Additional spectroscopic data from ESA's Mars Express and the ExoMars Trace Gas Orbiter will capture more emission lines across different wavelengths, providing more complete measurements of the nickel production rates, more detailed constraints on cyanide and carbon dioxide outgassing patterns, and more comprehensive data on what this thing actually consists of beneath its mysterious envelope of gas and dust. But right now, today, with all the data we currently have in hand from the best telescopes humanity has ever built, 3I/Atlas is demonstrably releasing industrial-grade pure nickel into space at exponentially increasing rates while showing absolutely no iron whatsoever in any spectral line. And despite months of analysis by dozens of research teams around the world, nobody has proposed a satisfying natural explanation that accounts for all the observations without invoking special pleading and unprecedented conditions. That's why Loeb felt confident enough to publicly rate this object at 60% probability of technological origin, a statement that will either vindicate his controversial stance or permanently damage his reputation depending on what the October data reveals. The scientific method demands we follow the evidence wherever it leads, even into uncomfortable territory that challenges our assumptions about humanity's place in the universe. If the data supports a technological hypothesis, we can't dismiss it simply because it makes us uncomfortable or threatens the established paradigm. But if the data ultimately supports a natural explanation, however exotic and unprecedented, then we have to accept that and learn from it. Either way, 3I/Atlas is teaching us something profound about the diversity of objects in our galaxy, about the limits of our current understanding, and about the importance of keeping an open mind when nature presents us with genuinely anomalous phenomena that don't fit our comfortable categories. Now let's talk about something that's causing absolute chaos on social media and bitter arguments in astronomy forums: something professional scientists are desperately trying to ignore or discredit without actually investigating. Amateur astrophotographers around the world are sharing images of 3I/Atlas that don't look anything like a typical comet, images that show structure and geometry where there should only be diffuse gas and dust. Instead of the soft, fuzzy, nebulous glow you'd expect from a ball of dirty ice evaporating in sunlight, some photographs reveal what appears to be hard edges, defined boundaries, geometric shapes that simply shouldn't exist in a natural object governed by the random processes of sublimation and outgassing. Michael Jagger and Gerald Raymond, two highly respected amateur astronomers with decades of experience and reputations for careful, accurate work, captured 3I/Atlas during the total lunar eclipse on September 7th from their observing location in Namibia, one of the darkest sites on Earth with minimal light pollution. Using professional-grade equipment that rivals what many universities own, they obtained images showing the object glowing an intense green color with distinctive bluish tinges around the edges, clearly indicating gas-rich composition with specific chemical signatures. The object was distinctly visible in both blue and green optical filters, confirming the presence of diatomic carbon and cyanide compounds that emit at those wavelengths. Professional astronomers acknowledged these particular images without hesitation because Jagger and Raymond are known quantities in the community, amateurs who follow rigorous procedures and produce reliable data. Their observations were legitimate, properly calibrated, and scientifically valuable for understanding the comet's gas production and color evolution. But it's the other amateur astronomers, individuals whose names haven't appeared in press releases and whose credentials aren't publicly known, who captured what's now being called the structured images in hushed conversations on Reddit and Twitter. These are photographs circulating widely on social media platforms, shared in astronomy forums, analyzed frame by thousands of curious observers, showing something that looks decidedly less diffuse and significantly more solid than professional images reveal. Something that appears to have edges where comets should have gradual fading, geometry where there should be chaos, organization where there should be randomness. These controversial images seem to show a more compact core beneath the gas envelope, something with defined boundaries that don't match the point spread function of stars or the extended fuzzy appearance of normal comets. The professional response to these amateur images has been swift, dismissive, and conspicuously lacking in scientific curiosity that should characterize how we approach anomalous observations. Instead of saying, "That's interesting, let's investigate with better equipment to verify or falsify these observations," the response has been immediate rejection. When pressed by amateurs seeking explanation, professionals cite a laundry list of technical issues. Motion blur from tracking errors as telescopes follow fast-moving objects across the sky, long exposure artifacts that can create false structure in images, telescope tracking issues that smear point sources into streaks and distort morphology, atmospheric turbulence that refracts light unpredictably. All technically valid concerns when imaging faint objects moving at high angular velocity thousands of times dimmer than naked eye visibility. Smearing effects and optical distortions are absolutely common problems in amateur astrophotography that can create misleading appearances. But here's what makes this situation genuinely fascinating and somewhat suspicious when you step back and look at the bigger picture. The ATLAS survey telescope that originally discovered 3I/Atlas, the automated system that first spotted this object among millions of asteroids and comets, uses mirrors only 20 inches in diameter. That's backyard amateur astronomer size, equipment that high-end hobbyists routinely own and operate from suburban locations. Advanced amateurs with 36-inch Dobsonian reflectors or 20-inch Schmidt-Cassegrain telescopes have equivalent or even superior light-gathering power and resolution. So when someone with comparable equipment captures unusual structure in their images, structure that doesn't appear in professional observations, why is there automatic dismissal without even attempting independent verification? Why aren't professionals saying, "Let's point Hubble or a major observatory at those exact coordinates during the same viewing geometry to see what's really there"? The lack of scientific curiosity is striking and suggests something deeper than simple technical skepticism. On Reddit's r/astronomy and r/astrophotography subreddits, debates are absolutely fierce with hundreds of comments on popular threads. Users are comparing images side by side, analyzing them pixel by pixel, applying their own processing techniques to raw data, trying to understand what's real and what might be artifact. Some images clearly show classic comet appearance. Diffuse coma developing around a barely resolved nucleus, faint tail streaming behind as solar wind pushes gas and dust away from the sun, gradual brightness fall-off following expected mathematical profiles. Those images look completely normal and match professional observations perfectly. But others show something harder to explain away with standard astrophotography artifacts, features that persist across multiple independent observations. Unusually compact cores that appear more solid than gaseous, irregular shapes that don't match the expected spherical or elongated morphology of comet nuclei, pixel patterns in properly calibrated images that don't follow the standard point spread function characteristic of stars or comets imaged through Earth's atmosphere. Half the commenters scream about image processing errors, insisting these amateurs don't know what they're doing and are being fooled by artifacts of their own creation. The other half are demanding someone with professional equipment replicate the observations to either verify these structures are real or definitively prove they're artifacts. That verification isn't happening, and that silence is deafening. Instead of offering to help check with better instruments, professional astronomers jump into discussion threads specifically to discredit the images without proposing any verification observations, dismissing the data without examining it carefully. One particularly controversial image circulating widely on X shows what multiple independent analysts describe as a more compact, less diffuse core than what Hubble captured in its official observations. The amateur who posted it claimed the image was taken with a 14-inch Schmidt-Cassegrain telescope, extremely common equipment in the amateur community, using 50 individual exposures stacked together to increase signal-to-noise ratio. That's absolutely standard practice for deep sky imaging, the same basic technique professionals use, just with smaller apertures and less sophisticated detectors. Professional astronomers who saw the image immediately cited a litany of possible problems. Atmospheric distortion from turbulent cells in Earth's atmosphere, tracking drift as the telescope mount imperfectly follows the object's motion, chromatic aberration from imperfect optics that focuses different colors at different distances, anything and everything to explain it away as user error or equipment limitations. But conspicuously, not one professional astronomer suggested actually pointing larger telescopes at the same coordinates to independently verify whether the structure is real. Not one offered to help the amateur improve their technique or verify their calibration. Just dismissal, just condescension, just, you don't know what you're doing, move along, nothing to see here. Here's what makes this entire situation genuinely strange and worth paying attention to despite the legitimate concerns about amateur image quality. The official Hubble Space Telescope image from July 21st, obtained with the most famous telescope ever built orbiting above Earth's distorting atmosphere, showed 3I/ATLAS with a distinct teardrop-shaped cocoon of dust, an elongated envelope that didn't match simple theoretical predictions. Even more strangely, the glow extended ahead of the object toward the sun rather than streaming behind as you'd expect from radiation pressure and solar wind. That forward-pointing structure violated basic expectations for how comet dust behaves under the influence of sunlight. Comet tails are supposed to stream behind, pushed away from the nucleus by solar wind particles and photon pressure, creating those magnificent sweeping arcs we see in photographs of great comets. But 3I/ATLAS was showing structure pointing the wrong direction, toward the sun instead of away from it. When professionals observed this anomaly with Hubble, they called it interesting and puzzling and worth studying further in press releases. They published papers analyzing possible explanations, maybe unusual dust grain sizes that respond differently to radiation pressure, maybe complex rotation creating asymmetric outgassing patterns, maybe viewing geometry effects that make the tail appear to point the wrong direction when it's actually oriented differently in three-dimensional space. All reasonable scientific responses to an unexpected observation. But when amateurs capture weird, unexpected structure in that same time period, they're immediately told they're seeing artifacts and don't understand image processing. The double standard is remarkable. Then on August 27th, Gemini South Observatory in Chile, one of the premier ground-based telescopes in the world, captured images showing the first clear evidence of a proper antisolar tail streaming behind 3I/Atlas in the expected direction. So between July and August, something fundamental changed about how this object was presenting itself to observers. Either 3I/Atlas genuinely started behaving more like a traditional comet as it heated up approaching the Sun, or our viewing angle shifted enough to reveal structures that were always present but hidden by geometry, or something else happened that we don't fully understand. Most of the controversial amateur photographs claiming unusual structure were taken precisely in that July to August window when even professional observations were showing anomalies that didn't fit standard comet models, when the object was behaving least like a normal comet and most like something strange. And here's another crucial data point that doesn't get nearly enough attention in mainstream discussions because it's buried in technical reports that few people read. NASA's SPHEREx infrared space telescope, designed to map the entire sky and study the large-scale structure of the universe, happened to observe 3I/Atlas in early August as part of its survey operations. SPHEREx has instruments specifically designed to detect and characterize the infrared emission from warm gas and dust, perfect for studying comets. Infrared light penetrates dust clouds and reveals the thermal signature of solid surfaces heated by sunlight. When you point an infrared telescope at a normal comet, you see extended diffuse emission from a large cloud of warming particles. Ice grains sublimating and releasing heat, dust particles absorbing sunlight and re-radiating it at infrared wavelengths. A big fuzzy blob of thermal emission with gradual brightness falloff. That's what every comet looks like in infrared without exception. But SPHEREx saw 3I/Atlas as a point source, a single concentrated dot of infrared emission with no extended structure whatsoever. That observation directly contradicts the comet model. If this object is a typical icy body with active sublimation creating the observed gas plume, SPHEREx should have detected diffuse infrared glow from carbon dioxide ice warming across the surface, from dust grains heated by absorbed sunlight, from gas molecules collisionally excited in the coma. Instead, a dot, a concentrated point of infrared emission more consistent with a relatively compact solid object than with a diffuse cloud of sublimating ice. That single observation from SPHEREx, largely ignored in popular coverage of this story, suggests something about the thermal properties or physical structure of 3I/Atlas that we don't understand and can't easily reconcile with natural comet models. So we have a very curious pattern emerging when you put all the pieces together. Professional telescopes capturing anomalies they can't fully explain with existing models. The wrong way dust tail, the unusual chemical composition, the nickel without iron. Amateurs capturing different anomalies that get immediately dismissed as incompetence without verification. Structured cores, hard edges, geometry. Both groups photographing the same object during the same anomalous time window when it demonstrably wasn't acting like comets are supposed to act according to decades of accumulated observational experience. The European Space Agency's Mars Express Orbiter and the ExoMars Trace Gas Orbiter, both currently studying Mars' atmosphere and surface, will photograph 3I/Atlas on October 3rd using cameras and spectrographs originally designed for planetary science, now repurposed for this unique opportunity. They'll be imaging from about 30 million kilometers away, not ideal distance for detailed morphology studies. ESA has already publicly stated in press releases that they don't expect spectacular images because the object will be incredibly small in their cameras. Less than a pixel in most of their instruments, just a dot among stars. But here's the crucial question nobody's asking in official channels. What if the amateurs were actually seeing something real? What if there genuinely is structure beneath the gas envelope, solid geometry obscured by the coma but occasionally visible when conditions align perfectly. The October observations from Mars orbit might not have sufficient resolution to settle this question definitively. We might need something closer, a dedicated flyby mission with instruments designed specifically for this object, cameras that can resolve surface details at scales of meters rather than kilometers. The truth is that we're flying partially blind through this encounter despite all our technological capabilities. Professional telescopes have extremely limited observing time, scheduled months in advance, allocated through competitive processes where dozens of proposals compete for each hour of telescope time. They can't be quickly redirected to follow up on amateur observations without going through bureaucratic processes. Amateurs have much more flexibility and can observe whenever weather and object position allow, but they have smaller telescopes and less sophisticated instruments that produce data professionals are quick to dismiss. And somewhere in that gap between professional capability and amateur flexibility, something unusual might be happening that neither group wants to fully acknowledge because the implications are uncomfortable regardless of the explanation. Because if the amateurs are correct, if there genuinely is non-natural structure visible in careful observations, then we're not talking about image processing artifacts or atmospheric distortion. We're talking about fundamentally rewriting what we thought we knew about interstellar visitors, about being forced to seriously consider possibilities that sound like science fiction. But if the professionals are correct and all the amateur structure is artifact, then we need to understand why so many independent observers using different equipment at different locations are all seeing similar artifacts that correlate with each other. Shared artifacts across independent observations suggest systematic problems with how we're interpreting data, which is itself interesting and worth investigating rather than dismissing. Either answer tells us something important. Either there's real structure we need to explain, or there's a systematic problem with amateur observations of fast-moving faint objects that we need to understand and correct. The refusal to investigate either possibility with the full power of professional equipment is itself suspicious and suggests motivations beyond pure scientific curiosity. We'll return to this question after October 3rd when Mars-based observations provide new data, but keep these amateur images in mind. They might turn out to be the first hints that something genuinely unusual is happening, or they might turn out to be excellent examples of how human perception and pattern recognition can mislead us when analyzing noisy data. Time will tell, and the data will decide. Now let's discuss something that sounds like science fiction but is actually based on rigorous orbital mechanics and statistical analysis by multiple independent research teams. In less than 48 hours from right now as you're watching this, 3IATLAS will pass within 18 million miles of Mars, a distance that sounds enormous but is actually remarkably close in cosmic terms. For comparison, that's only about 1/5 the distance between Earth and Mars when they're at closest approach, near enough that spacecraft orbiting Mars can obtain detailed observations with instruments designed for studying the Martian surface from just hundreds of kilometers altitude. NASA's press releases emphasize that this is a safe flyby, that there's zero risk of impact or disruption to Martian operations, and that's absolutely true. But here's what they're carefully not discussing in those sanitized public statements. The minimum orbit intersection distance, the absolute closest point where 3I/Atlas's trajectory intersects Mars's orbital path around the Sun, is only 1.7 million miles. When Avi Loeb calls this remarkable fine-tuning in his technical blog posts, you need to understand the full implications of that precise phrase. When a Harvard astrophysicist known for careful word choice uses remarkable fine-tuning to describe an orbit, he's saying something profound about probability and chance. This isn't a random close approach that happened to occur because space is big and Mars orbits where it orbits. This is precision alignment that suggests either extraordinary cosmic coincidence or something else entirely. The high-rise camera aboard NASA's Mars Reconnaissance Orbiter, the highest resolution camera humanity has ever sent to another planet, will image 3I/Atlas with a resolution of 30 kilometers per pixel on October 3rd. That might not sound impressive compared to the stunning images of Mars' surface where high-rise can see individual rocks and layered terrain, but for observing an object 30 million kilometers away, it's actually remarkably detailed. That resolution is sufficient to separate the solid nucleus from its surrounding dust cloud and measure the actual surface area reflecting sunlight. It's detailed enough to determine whether this object is really 5 kilometers across, as Loeb's latest mass calculations predict, or something smaller concealed in larger dust envelope. And here's why that size determination matters so critically. If the nucleus truly is that large, 5 kilometers or more in diameter, then the natural comet explanation collapses entirely under the weight of statistical improbability. Based on our best understanding of the limited reservoir of rocky and icy material in interstellar space, informed by surveys of dust density and theoretical models of planetary system formation, we should have detected roughly 100,000 smaller interstellar objects on the scale of Oumuamua, just a few hundred meters across, before ever finding something as massive as 3I/Atlas if the size distribution follows the same power law scaling we see everywhere else in astronomy. But we found exactly 3 interstellar visitors total in all of human history: Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas. Both previous visitors were relatively small, kilometer-scale objects at most. This one is supposedly 5 times larger in diameter, which translates to 125 times more volume and potentially thousands of times more mass depending on density. The statistics simply don't support finding something this rare before cataloging the population of more common smaller objects. It's like discovering a blue whale on your first ocean expedition before you've ever seen a sardine. But here's where things transition from merely improbable to genuinely disturbing in ways that make this feel less like science and more like science fiction. Loeb calculated, using straightforward orbital mechanics that any advanced undergraduate physics student can verify, that if 3I/Atlas deployed a smaller precursor probe at some point during its approach, a scout craft perhaps tens of meters across traveling ahead of the main body by approximately 30 million kilometers, that forward probe could intercept Mars on October 3rd or during the week immediately preceding the main object's flyby. And before you dismiss this as wild speculation completely disconnected from evidence, understand the truly terrifying part of this scenario. Earth-based telescopes, even our most powerful observatories, fundamentally cannot detect objects smaller than roughly 100 meters diameter at Martian distances. That's not a limitation of our technology that we can overcome with better cameras or longer exposures. It's a hard limit imposed by physics. The amount of sunlight reflected from small distant objects versus the sensitivity of our detectors and the overwhelming brightness of background stars. An object 100 meters across at Mars distance reflects so little light that it's literally invisible against the noise of the sky background. That happens to be almost exactly the size scale of spacecraft that humanity has launched into deep space. Voyager, Cassini, New Horizons, all our ambitious interplanetary probes fall right around that size range. Any hypothetical precursor probe, any scout craft sent ahead to survey Mars in detail before the main vessel passes by, would be effectively invisible to us using current detection methods. We'd have no way of knowing it was there until it was too late to observe it properly. The idea isn't nearly as crazy or far-fetched as it initially sounds when you think about how we would design such a mission with our own technology if we had the capability for interstellar travel. If you were tasked with designing an interstellar mission to survey a planetary system light-years from home, would you send one massive ship on a trajectory that passes every planet of interest? No, absolutely not. You'd send a mothership carrying multiple smaller reconnaissance probes, each designed to break away and vector toward specific targets of interest, gather detailed data from close range, and either transmit findings back to the mothership or rendezvous later to download information. The main craft would follow a safe trajectory through the system, perhaps not approaching any planet too closely to avoid gravitational perturbations that might affect its primary mission, while the smaller disposable probes do the risky close-up work. It's exactly the mission architecture we'd use if we had the propulsion technology and the resources. Multiple targets, multiple probes, efficient survey strategy. And the trajectory of 3I/Atlas makes this disturbingly plausible from an engineering perspective. The object's current path through our solar system requires only a 10 to 15 km per second velocity adjustment during September to reduce its closest approach distance to Mars down to essentially zero, to convert what we're observing as a distant flyby into an actual intercept where something could be delivered to or deployed at Mars. For any technological object with even modest propulsion capability, that's a trivial maneuver, barely noticeable against the background orbital velocity. 10 kilometers per second is only about 2% of the object's total velocity relative to the Sun, easily achievable with high-efficiency ion drives operating over weeks or months. But for a natural comet, for a passive object governed purely by gravity and the weak rocket forces from sublimating ice, that velocity change is completely impossible. The ejection speed of icy fragments from sublimating comets, measured directly by James Webb Telescope observations showing individual particles leaving the nucleus, is only about 400 meters per second at most. You'd need to eject more than 100 times the object's total mass at that speed to achieve a 10 km per second velocity change, which obviously can't happen. Natural comets can't steer. They follow gravity and receive tiny nudges from outgassing that amount to meters per second over months, not kilometers per second on command. NASA's Mars Express Orbiter and the ExoMars Trace Gas Orbiter, both sophisticated spacecraft operated by the European Space Agency currently studying Mars from different orbital positions, will also observe 3I/Atlas on October 3rd using multiple instruments not originally designed for this purpose. High-resolution cameras capable of imaging Martian surface features from orbit, spectrometers that normally analyze atmospheric composition, particle detectors designed to study the solar wind's interaction with Mars' thin atmosphere, all being repurposed to study this unexpected visitor. They're designed to characterize the Martian environment from orbit, but they'll attempt to characterize this comet's volatile activity and composition from 30 million kilometers away, 100 times farther than their normal operating distance. ESA's official press releases state the instruments will attempt to measure the comet's gas production rates, identify specific chemical species in the plume, and characterize how the object is responding to increasing solar heating as it approaches perihelion. Standard scientific objectives that any planetary scientist would propose. But there's a secondary objective that hasn't been advertised in public statements. A goal that only appears in technical planning documents if you know where to look and what terminology to search for. HiRISE won't just image 3I/Atlas itself, the bright concentrated nucleus and its surrounding coma. It will scan the space around the object, particularly the region ahead of the nucleus along its trajectory, looking for anything that might be traveling in formation with the main body. Looking for smaller objects that separated earlier and are now approaching Mars on slightly different trajectories. Looking for precursor probes. Loeb suggested this explicitly and publicly in his detailed blog posts that most media coverage ignored. Use HiRISE's wide-area survey capability to search for objects preceding 3I/Atlas that might arrive at Mars before the main body. Objects that couldn't get there through natural ejection from sublimating ice but could absolutely get there if they were independently propelled. If materials from 3I/Atlas reach Mars in October, materials that couldn't possibly have gotten there through natural sublimation and ballistic ejection, that would be an unambiguous signature of technology, of deliberate targeting, of intelligence behind the trajectory. The timing of all this is deeply suspicious in ways that make paranoid speculation feel almost justified. 3I/Atlas reaches its closest approach to Mars exactly 1 week before it disappears behind the Sun from Earth's perspective, vanishing into solar glare where we can't observe it for 2 full months. We get precisely 1 good observational window with spacecraft at Mars to see what this object does during close planetary approach, and then the main body goes dark, hidden, unobservable. If you wanted to deliver something to Mars with minimal chance of detection and detailed study, this would be the perfect timing window. Deploy your probe during the October 3rd close approach while Earth telescopes are watching the main object. Then let the mothership hide behind the Sun for 8 weeks while the deployed probe does whatever mission it was designed to accomplish. By the time 3I/Atlas emerges from behind the Sun in December, any secondary objectives would be complete, any probes would have landed or deployed, and we'd be left analyzing trajectory changes that might or might not reveal what actually happened during those 2 hidden months. NASA's Curiosity and Perseverance rovers currently exploring Mars' surface might attempt observations as well from their ground-based perspective, though the comet will be incredibly faint even during closest approach, possibly at the limit of what their navigation cameras can detect against the brightness of Mars' dusty sky. The Mars Reconnaissance Orbiter with HiRISE is really our best shot at obtaining detailed imaging that could resolve the nucleus from its dust envelope and potentially detect any anomalous objects traveling in formation. And then there's the question that nobody in official channels wants to discuss openly. What's the protocol if they actually find something? If HiRISE captures an image showing multiple distinct objects where there should be only one comet, or if the trajectory shows evidence of maneuvering that can't be explained by natural outgassing, or if anything appears in the data that suggests artificial activity rather than natural processes, what happens next? Do mission scientists announce immediately through NASA's Public Affairs Office? Do they verify through additional observations from other spacecraft to make absolutely certain before making extraordinary claims? Do they classify the data under national security protocols and brief government officials before public release? There's genuinely no established procedure for this scenario because nobody seriously planned for the possibility despite decades of SETI research. The protocols for detecting extraterrestrial intelligence have always focused on radio signals that we might receive from distant civilizations or optical beacons that advanced societies might use to announce their presence, not on physical craft passing through our solar system exhibiting technological signatures. We're improvising in real time. In less than 24 hours from when you're watching this video, we'll begin to get answers to questions that have haunted humanity since we first looked up at the stars and wondered if we're alone. We'll know if those amateur astronomers were capturing genuine structure in their backyard telescopes or seeing artifacts of their imaging process. We'll know if the nickel without iron signature truly means what Loeb thinks it means or if there's some exotic natural explanation we haven't considered. We'll know if that 1.7 million mile minimum orbit intersection distance with Mars represents remarkable cosmic coincidence or something else entirely. Or we'll see a perfectly normal comet nucleus consistent with natural formation, and all the speculation will collapse into embarrassed silence as scientists who went out on limbs try to salvage their reputations. But either way, October 3rd, 2025 is a date that might end up in history textbooks studied by students centuries from now. It's either the day we confirmed 3I/Atlas as an exotic but ultimately natural interstellar comet from a dying star system billions of light-years away, or it's the day everything changed, the day humanity had to confront the reality that we're not alone, that we're being watched, that visitors from other worlds have entered our solar system with purposes we can't yet comprehend. The scientific observations will continue for months after this critical flyby date. As 3I/Atlas emerges from behind the Sun in early December, ground-based telescopes around the world will track its outbound journey, watching to see if its trajectory matches gravitational predictions or if there are unexplained deviations suggesting propulsion. The James Webb Space Telescope has additional observation time scheduled for December to conduct follow-up spectroscopy and see how the chemical composition has evolved after perihelion passage. ESA's Jupiter Icy Moons Explorer spacecraft, currently en route to the Jovian system, will attempt long-distance observations when the comet passes relatively close to Jupiter in March 2026. Every data point matters. Every observation either supports or challenges our understanding. And the scientific community is watching this unfold with a mixture of excitement and genuine anxiety about implications. What makes 3I/Atlas truly special, regardless of whether it's natural or artificial, is what it represents for the future of astronomy and our search for life beyond Earth. This object has demonstrated that interstellar visitors do pass through our solar system with some regularity. We've now detected 3 in just 8 years. Oumuamua in 2017, Borisov in 2019, and now Atlas in 2025. That's a detection rate far higher than early theoretical predictions suggested, implying that interstellar space between stars isn't as empty as we once believed. There could be trillions of these wanderers in our galaxy, ejected from their parent systems billions of years ago, traveling endlessly through the cosmic dark until gravity occasionally brings them near another star. Each one is a messenger from elsewhere, carrying information about other planetary systems, other stellar environments, other corners of the galaxy we can never visit with current technology. They're natural interstellar probes, whether or not any intelligence designed them, bringing us samples and data from places we can only dream of reaching. The Vera Rubin Observatory that came online in 2025 and immediately began discovering thousands of asteroids is going to revolutionize this field over the next decade. Its wide-field camera and rapid survey cadence mean it will detect interstellar objects much earlier in their approach, giving us months or even years of observation time instead of the rushed weeks we've had with previous visitors. When the next interstellar object arrives and we spot it while it's still in the outer solar system beyond Jupiter's orbit, we might actually have time to launch a dedicated flyby mission to intercept it and study it up close with instruments specifically designed for the task. Imagine a spacecraft rendezvousing with an interstellar visitor, matching its velocity, flying alongside for weeks or months while cameras and spectrographs gather data at close range. That's the future of interstellar object research, and it's not science fiction anymore. The technology exists. We just need the lead time to plan and execute such missions. 3I/Atlas has also sparked renewed interest in Project Lyra and similar mission concepts that propose using gravitational assists and advanced propulsion to chase down interstellar visitors after they're discovered. The original Lyra studies focused on Oumuamua and whether we could launch a spacecraft fast enough to catch it before it left the solar system forever. The answer was yes, barely, using a Jupiter gravity assist combined with nuclear-powered propulsion and solar sails. The mission would take decades and cost billions, but it's technically feasible with existing technology. Now mission planners are updating those concepts for 3I/Atlas, calculating trajectories and delta-v requirements, preparing proposals that might get funded if public and scientific interest remains high enough. There's a window of opportunity here, a chance to answer fundamental questions about these objects before they disappear into the interstellar night for another million years. But beyond the scientific and technical considerations, 3I/Atlas has reignited philosophical and existential questions that humanity has grappled with throughout recorded history. Are we alone in the universe? If we're not alone, how do we recognize the signs of other intelligences when we encounter them? What does it mean for humanity's future if we discover we're just one civilization among countless others scattered across the galaxy, perhaps one of the youngest and least advanced? These aren't abstract philosophical puzzles anymore. They're questions that might be answered by analyzing spectrographic data and orbital mechanics, by pointing our best instruments at a fast-moving icy object and determining whether the patterns we see are natural or designed. The boundary between science fiction and science fact has never been thinner than it is right now. In October 2025, as spacecraft at Mars turn their cameras toward this enigmatic visitor and prepare to gather data that might change everything, I want to take a moment here to talk about why understanding this content matters so deeply, why paying attention to scientific discoveries like this is crucial not just for personal curiosity but for our collective future as a species. We live in an era where humanity's technological capabilities are advancing exponentially, where questions that were pure speculation for our grandparents are being answered with hard data during our lifetimes. The decisions we make about space exploration, about funding scientific research, about how we respond to discoveries that challenge our assumptions, these decisions will shape the trajectory of human civilization for centuries to come. If 3I/Atlas turns out to be evidence of extraterrestrial intelligence, whether a probe or an artifact or something we haven't imagined, our response to that discovery will define us as a species. Do we react with fear and suspicion, building walls and weapons? Or do we react with curiosity and openness, building better telescopes and preparing for potential contact? The scientific method that guides this investigation, that commitment to evidence-based reasoning and willingness to revise conclusions when new data emerges, represents the best of human intellectual achievement. Supporting that process, understanding it, demanding it from our institutions, that's how we ensure our future as a spacefaring civilization capable of meaningful discoveries. So if you've made it this far in this incredibly detailed dive into the 3I/Atlas mystery, I need you to do something crucial right now. Leave a comment below saying "Atlas opened my eyes," to show you've absorbed all this scientific evidence and you're ready for whatever comes next. That comment tells me you're part of the community that cares deeply about these discoveries, that you're willing to look at challenging data and wrestle with implications that might be uncomfortable. Leave your like on this video to push it to more people who need to understand what's happening above our heads right now. The algorithm rewards engagement, and this information needs to reach as wide an audience as possible before the October observations begin. Subscribe and hit the notification bell because when those high-rise images come down from Mars Reconnaissance Orbiter, when ESA releases their spectroscopic data, when professional analyses start appearing in journals, I'll be breaking it all down here first with the same level of depth and scientific rigor you've experienced in this presentation. You won't want to miss that follow-up coverage because this story is just beginning, not ending. And watch the next video that's appearing on your screen right now where I dive into even more anomalous objects in our solar system that mainstream science struggles to explain, phenomena that might be connected to what we're witnessing with 3I/Atlas in ways we're only beginning to understand. The universe is vast beyond human comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars, most of those stars surrounded by planetary systems where chemistry and evolution might have produced countless forms of life we can't imagine. The statistical argument has always suggested we can't possibly be alone, that the sheer scale of the cosmos makes the existence of other intelligences essentially certain. But statistics aren't the same as evidence. Until we have data, actual observations that we can analyze and debate and verify, the question remains open, unanswered, a source of speculation rather than knowledge. 3I/Atlas might be the object that bridges that gap between statistical probability and empirical confirmation, between believing we're not alone and knowing we're not alone. Or it might be an extraordinary example of how nature can produce phenomena so bizarre and unexpected that they mimic artificial signatures, teaching us humility about the limits of our current understanding and pushing us to expand our models to accommodate greater complexity and diversity. Regardless of which answer the data ultimately supports, the process of investigation itself is valuable and ennobling, representing humanity at its best. Scientists from dozens of countries collaborating to observe this object, sharing data freely across borders and institutions, subjecting their interpretations to rigorous peer review, following evidence even when it leads to uncomfortable conclusions. This is the scientific method in action, the systematic approach to understanding reality that has given us every technological marvel we enjoy and every genuine insight into nature's workings. It's messy and contentious with fierce debates about interpretation, but it's also self-correcting and progressive, gradually converging on truth through accumulated evidence. That process deserves our respect and support even when, perhaps especially when, the questions being investigated seem to challenge fundamental assumptions about our place in the cosmos. As we approach the October 3rd observations with a mixture of anticipation and anxiety, it's worth reflecting on the historical parallel with previous paradigm shifts in human understanding. When Copernicus proposed that Earth wasn't the center of the universe, when Darwin suggested humans evolved from earlier species, when Hubble demonstrated the universe extends far beyond our galaxy, each discovery was initially controversial and deeply unsettling to prevailing worldviews. Each one met fierce resistance from established authorities who had invested heavily in older models. But evidence prevailed, observations accumulated, and eventually the new paradigm became accepted as the obvious truth that should have been recognized all along. If 3I/Atlas proves to be artificial, if October observations provide compelling evidence of extraterrestrial intelligence, we'll be living through another of those transformative moments when human self-understanding fundamentally changes. Our descendant will look back at October 2025 the way we look back at 1543, when De Revolutionibus Orbium Coelestium was published, or 1859 when Origin of Species appeared, or 1929 when Hubble's distance measurements revealed the universe's true scale. They'll see this as the moment when humanity definitively learned we're not alone, when cosmic isolation gave way to cosmic companionship, when we joined whatever community of intelligences inhabits this galaxy. Or our descendants will look back and smile at our excitement over an exotic comet, amused by how close we came to believing something extraordinary was happening when it was just nature being weird in ways we hadn't anticipated. They'll study 3I/Atlas in astrophysics courses as a cautionary tale about pattern-seeking brains finding significance in random data, about the importance of maintaining skepticism and demanding extraordinary evidence for extraordinary claims. Either future is possible. The data will decide. And that's the beauty and power of the scientific method, its commitment to following evidence wherever it leads without prejudice about preferred outcomes. The universe doesn't care about our hopes or fears, our desire to find companionship among the stars, or our anxiety about what such contact might mean. Reality is what it is, and our job as rational beings is to observe carefully, reason clearly, and accept whatever truths emerge from honest investigation. So we wait for October 3rd with patience and open minds, ready to receive whatever answers the universe chooses to provide through those precious observations from Mars' orbit. We prepare to have our assumptions challenged, our worldviews possibly shattered, our understanding of reality expanded in directions we can't yet imagine. This is what it means to live in the 21st century, to inhabit a moment in human history when questions that have haunted us since we first became conscious might finally receive definitive answers. The universe is speaking to us through objects like 3I/Atlas, sending messages across the unimaginable gulfs between stars. Our technology has finally advanced to the point where we can receive and decode those messages, where we can study these cosmic messengers in detail and extract their secrets. What we learn might comfort us or terrify us, might answer old questions or pose entirely new ones, might confirm our loneliness or herald our introduction to a much larger community. But learn we will, understand we must, and grow we shall from whatever truth the data reveals. Thank you for joining me on this deep investigation into one of the most significant astronomical events of our time. Thank you for your patience with the scientific detail, your willingness to wrestle with complex implications, your commitment to understanding rather than just consuming sensationalized headlines. This is how science should be communicated. Thoroughly, honestly, with appropriate uncertainty acknowledged and extraordinary claims treated with appropriate skepticism while remaining open to extraordinary evidence. If you found value in this analysis, share it with others who care about these questions, who wonder about our place in the universe, who want to understand what's really happening as 3I/Atlas passes through our solar system. Knowledge grows through sharing, understanding deepens through discussion, and humanity advances through collective effort to comprehend the cosmos we inhabit. Until next time, keep watching the skies, keep questioning assumptions, and keep following the evidence wherever it leads. The universe has secrets to reveal, and we're fortunate enough to live in an era when revealing those secrets becomes possible through instruments and methods our ancestors could never have imagined. What a time to be alive! What a privilege to witness these discoveries! What an opportunity to participate in humanity's grand adventure of cosmic exploration and understanding. Clear skies, everyone, and may the data bring us truth, whatever that truth might be.